Okay, so this looks really terrible. Sorry about that. I don't know why it shows up so bad, but this is chapter 1. And we're going to be starting out looking at alkanes. So organic chemistry is just the study of the structure, properties, composition, reactions of carbon-containing compounds. So everything we're going to be looking at contains carbon. And carbon forms 4 covalent bonds. And covalent bonds just means that they share electrons. So that's something, we learn in intro to chemistry. And they share those single bonds with 4 atoms. That's not always the case. We're going to look in the next chapter at double and triple bonds. But for now, just for alkanes, we're looking only at single bonds. So this makes carbon tetravalent. Again, that just means it has those 4 bonds. So some examples here are methane. Methane has 4 hydrogens around the carbon. And then ethane, we have 2 carbon atoms that are combined there in a single bond. And then we have the hydrogen around those carbons. So they still have 4 single bonds around each carbon. So again, carbon can have double and triple bonds. Here's some examples of that. We have ethylene and with the double bond, and then we have the triple bond. So we'll get more into that with chapter 2, but we aren't really going to cover that right now in chapter 3. But the main thing to see is that even with the double or the triple bond, they still have 8 valence electrons. So if you remember from intro chemistry, the goal is to get the octet, which is the 8 valence electrons. So that still is happening with the double and the triple bonds. So in general, if carbon has 4 groups attached to it, so a group can be an atom or a group of atoms that are attached to the carbon. So if there's 4 groups attached to the carbon, it's tetrahedral. So for all single bonds around the carbon, it'll be tetrahedral shape or geometry. If the carbon has 3 groups attached to it, so usually that means it has a double bond, then it will have the trigonal planar shape. If carbon has 2 groups attached, so that will have the triple bond with it, it'll have a linear shape. So just some differences here between organic and inorganic. Organic molecules are molecular compounds, and usually when we're talking about inorganic molecules, we're talking about ionic compounds. So organic molecules contain molecular compounds. They're held together by those covalent bonds, so they share electrons, and they have low boiling points, low melting points. They're mostly insoluble in water, so that means they mostly don't dissolve in water, and they don't conduct electricity. So the opposite pretty much is inorganic molecules. So inorganic molecules are made up of ions, so the cation and the anion, and they're held together by their charges. So the example there is sodium chloride. They have high melting points, high boiling points, and they will most likely dissolve in water. Now, not all of them will, but usually they are soluble in water, and they do conduct electricity. So basically the totally opposite of what we said organic molecules are. Organic molecules can be either polar or nonpolar, depending on what the carbon atoms are bonded to. So if I just have carbon and hydrogen, it's going to be nonpolar because carbon and hydrogen have the same number of electronegativity. So that means that they will share the electrons equally and they are not pulling one way or the other. But if I have something that's very electronegative attached to the carbon, like in the example here, chloromethane, then the chlorine is going to pull the electrons to itself, and it's going to form that polar bond and make the molecule polar itself. So again, if it just has carbon and hydrogen, then overall it's just going to be non-polar. Nobody's going to be pulling the electrons one way or the other. Organic compounds are classified into families according to their structural features. And these groups of atoms have similar chemical behavior. So table 1 in your book gives a list of the important families, and we call them functional groups. The chemistry of the molecule is determined by the functional group. So it's determined by the functional group in the molecule and not its size or complexity. So if you have, this massive molecule and it has a functional group on it, then we're, really the chemistry is determined by that functional group. So we're going to be looking at these. We're going to be talking about what they're called, but really we're going to be studying each of the functional groups throughout the semester in the different chapters. So for now, we just kind of want you to recognize them. And then later on, you'll be more familiar with it as we continue to talk about them throughout the chapters. So here's an example of the functional group. So we have, 2 carbons. Let me do this real quick. So we have these 2 carbons right here. They're not a part of the functional group. We just call those a hydrocarbon chain. And you can see that over here represented with the R. So the functional group is actually in the red box. So we'll talk about here in just a minute what that name of the functional group is called. So you'll need to be able to recognize these groups. So first up, we're going to be talking about alkanes mostly in this chapter. And I already mentioned they have only single bonds, and we're only looking at carbon and hydrogen. We'll throw a few halogens in there with them, but for the most part, just carbon and hydrogen. And then the next chapter, we're going to be talking about alkenes. So they have a double bond within the carbon-carbon, or between the carbons, they'll have a double bond. So 1-butene is listed here. And then the alkynes have the triple bond between the carbons. And it's almost the same name, 1-butyne. So again, we'll be getting into alkenes and alkynes in the next chapter. But just know for now, alkenes have a double bond, alkynes have a triple bond. Okay, aromatic rings contain a 6-membered ring of carbon atoms. So each point on here, each point, I'm not circling, there we go, has a carbon that represents in the point. Okay, so a ring of carbon is possible. We'll talk about the different types of aromatic rings and all that. And again, that's coming later in chapter 2. And then we have alkyl halides. So we'll have halogens that are attached to the carbon chain. So we have chlorine there attached to the carbon chain. An alcohol group is an OH, so an OH group bonded to the carbon chain. And then when I have an oxygen that's in between the carbons in the carbon chain, that's called an ether. So again, we're just recognizing these right now. We're not, we'll get more in depth with them in the later chapters. Then we have an amine when you have a nitrogen bonded to the carbon. And then an aldehyde, we have a carbonyl carbon, so that's the carbon and the double bond to the oxygen, that's the carbonyl carbon. And when that's attached to a hydrogen, then you have an aldehyde. So, whoa, didn't mean to do that, or that. Let's try that again. Okay, so this right here doesn't have to be an H. It can be an R group. So that could be a long carbon chain. It could be, something different. It doesn't have to be an H. So what we're really focused on is what's circled in the red. Okay, and then a ketone will have a carbonyl carbon bonded to two different carbons. So we have a carbon here and a carbon here. Okay, so that's what makes it the ketone. Okay, carboxylic acid, we have the carbonyl carbon attached to a OH group. So that's a carboxylic acid. So that wouldn't be considered just an alcohol like we saw earlier with the OH attached to the carbon chain. And then, there it is. An ester is a carbonyl carbon attached to an OR group. Okay, so OR, oh, for goodness sake, I'm sorry. Here we go, let's try that again. So, it doesn't matter what this section is, right? So that's the R we're talking about. So that can represent, one carbon or several carbons, but, the O right there with it attached to the carbons in the carbonyl carbon is what represents it as an ester. And then we have the amide. Is the carbonyl carbon attached to a nitrogen group. And hydride, we have two groups. So we have two carbonyl carbons attached to an oxygen and the carbon chains. So we'll talk more about that later. And then we have the thiol, where we have the sulfur and the hydrogen attached to the carbon chain. And then we have the disulfide bond, where we have two sulfurs attached or connected there in the chain, the carbon chain. And then we have the sulfide, just one of the sulfurs in the carbon chain. So those are a little bit easier to recognize with them being the sulfurs. But again, you don't need to draw these structures, you just need to be able to recognize them and point them out. We will cover them more in depth in the chapters to come.